So the final speaker, we move now to an application use of grids. Leopoldo Benacchio from, I got it wrong, the Astronomy Institute in, apologise. Leopoldo's going to talk about the astronomy use of grids, and there are many aspects of it that can really push the network. I happen to know because I work a lot with radio astronomers. I don't know whether that will feature in the talk today.
Okay, I will talk about the switch of astronomy from networks to the grid, but let me express you before to speak about networks what really astronomy is, because generally in the mankind mind astronomy is supposed to be quite a romantic science, or better saying what I want to say is well represented by these prints that is a false, an historical false, because it has been made, is not a Renaissance print, but it has been made more or less 100 years ago by Camille Flammarion. And maybe people not here, of course, think that we spend all the night looking at the sky with this fashion instrument like this. This is 200 years ago fine telescopes in the Padua Observatory, my observatory. And what really astronomers are in the mind of people is well represented by the small bill of my Péter. I left to pay more or less €1. These are liras, but anyway, is more or less €1. And as a memorandum, you wrote not my name, but what in his mind I am, that is an astrologer, that in Italian is very close to fortune teller, and doctor, because academic. So astronomy has a longer history with the machinery and also with communication. In every year, astronomers have used the up-to-date supercomputer, the calendarial machine, as Stonehanger we have all over the world, are in effect calculators for the calendars. We could speak about plenty of examples, but maybe one of the most interesting is the Babbage case and the relationship between Babbage and the ephemerides problem. Ephemerides are tables, very boring tables with star positions. Very important for astronomers, but very important also before the global positioning system era for the sailors. So the effort to have better ephemerides was an incredible, tricky computational problem, and this is one of the reasons why Babbage developed the scheme of his famous analytical machine. Communication also has a long history in astronomy, because you have to think that maybe we are in the realm of the probably more ancient science. So this letter, for example, and the letter was the fastest way to communicate at the epoch, is the letter of Galileo Galilei announcing to the Prince of Florence the discovery of the 4 major Jupiter satellites, the so-called Galilean satellites. And this letter is in some way the first important milestone of the scientific mythos of all the science. At the beginning of the last centuries, astronomy became the first, maybe, globalized science because of a system of communication via the most effective way at that era, that is the telegrams. But why communication is so important in astronomy from centuries? Because the sky moves, or better, seems to move. Okay? So a new astronomical phenomena can be followed hour after hour in different observatories in different parts of the world. So it's very simple, but it's very important. In the last decades, we are going farther and farther from the civilization because of the incredible increase of light pollution. Okay? It's not primary pollution, it's not for our health maybe, but is extremely dangerous for scientific instrument. Best places now are mountains in the middle of a desert. You have to think that also there is an incredible increase in the sensitivity of the instruments. We have now, this is the mirror of the 8 meters telescope, the most important installation in the world, that is European Very Large Telescope in the Paraná Desert in Chile. And there are also, you can see also the police in order to avoid theft of the 8-meter mirrors. With this telescope, we can easily see if a man or if a man in Mars is lighting a cigarette. So this site is 2.5 hours of Piper fly from the first light bulb. And in the world, there are no more than 5 places where to put new generation telescopes. And they are extremely expensive. Anyway, the weather is generally good in these places, and the partnership is also interesting. Maybe it's also not clear that we are living a revolution that can be compared with the revolution of Galileo Galilei some centuries ago and Newton. Why? Mainly, for example, because of the increasing of the CCD technology, we passed from the 900 pixels CCD of 20 years ago, 20 years ago of the ISO satellites, to the 900 million pixels of the next generation, that is next year, CCD cameras in Paraná, in Chile, European camera. Supercomputers are encouraging us to develop new models of forecasting. New modeling of theories are changing day by day the way in which we work and the precision we can have in the forecasting. And also the data storage technology has increased in order to store all these incredible amount of data. But maybe the most important reason why we need a grid and the networks is that now we know an incredible amount of phenomena. We know very well with respect to 20 years ago. But we are not able to understand more or less nothing. Why? Because after 2 millenniums at least, we are now in a position to go outside atmosphere. And as you know, atmosphere is stopping 98% of the radiation that is coming from heavenly bodies, from celestial bodies. This is good for us as men, but is disgusting for us as astronomers, because it's like to study the DNA losing 98% of the information. Very tricky, very difficult. Now to go to outside the atmosphere with space astronomy allow us to do not more physics, but a completely different physics. Look at this. We have been confined for millennia to see this galaxy, our galaxy. That is what I see in visible light with my eyes from ground. Now I can see it in X-ray. So looking at the extremely high energy phenomena, infrared, microwaves, and so on. And these are all chunks of a puzzle that we are not able at the present to understand. So to understand this puzzle and to be able to reconstruct it, we need grid. Why? Astronomy, as you know, is probably one of the first science with high energy physics in the business of the network. This is an old chart of the Italian astronomical observatories and universities map, and has been maybe one of the first all-digital science. Why? Because he developed an end-to-end cycle of the work that is typical of the network, from observation preparation to data reduction, and then archiving, and then look at the archive, and then modeling, because unfortunately we have 10% of theoreticians also, and then distributing literature and so on. Now we are considering the grid, and is for us an important change, because first we don't work longer at the system level. We switched to the application level. We left grid to engineers, people, and people connected to the to informatics. A network allowed us to have strong communication, and the web allowed sharing on the communication. We are in depth considering what WhyGRID will mean for us. Will be a complete change of metaphor, that is sharing the work or not. And what about the steps to reach this goal? We started in the framework of the Italian grid for the research with with a mini grid. Let me say a mini grid. 3 observatories are engaged presently, and we hope to have 7 observatories in the general grid. But this is not the point. It's not the point, the number of machines, number of observatories, and so on. The main point is to consider how typical astrophysical application can be ported into the grid. And if the astrophysical application will give some indications on constraints for the developing of the grid. We have 3 important case studies. The first one is database and astrophysical archives case. Planck is an ESA satellite. I will speak briefly after. So, and TNG is the telescope in the image, is the National Galileo telescope, You know that in Italy, the largest telescope in each epoch is named Galileo, is a time invariant. So this is the present-day Galileo telescope. And the GUIDE's catalog 2, that is the largest astronomical catalog presently existing, is 20, oh, I don't remember, anyway, 20 billion records catalog of star positions and properties. The second interesting case study is image reduction and analysis of the VST survey. What is VST? VST is a small telescope in Paranal. You see the four elephants, 8-meter elephants, European telescopes in Paranal. VST is a small one and will act as a pilot fish for the Giants telescope, with the largest CCD camera existing for the moment, the 32,000 square CCD camera. So you can imagine the amount of data that will flow from this camera, and also the importance of the survey of the sky that will be done. Third and last is maybe the more tricky and also the more ambitious. Can a telescope be considered as part of a grid? Telescope is an instrument, is a completely computer controlled. We have now remote observing application. We can use the telescope in Chile with a peer-to-peer application in Bavaria, in München, where the headquarters of the European Southern Observatory are. And we are waiting, of course, great benefits for astronomers in case of positive results. Let me show you just a little bit in depth the case of Planck. Planck is a satellite, an European satellite that will fly in a couple of years and will map the microwave universe, that is the universe after some seconds from the Big Bang. You can see on the right a simulation between our present upper knowledge of the microwave universe and the supposed Planck vision of the same universe in lower. As you can see from this slide, this could be considered as an ideal case for the porting a grid, because the time interval is 4 years, so is not enough time to work. It's distributed over several sites, several institutions, several countries with different scientific approaches, and so on. Last, let me show you an important application radio astronomers are studying that will pose severe condition to the networks. Radio astronomy studies the object in the sky at a radio wavelength. This is extremely important because several phenomena are evident only in this wavelength range. The main problem with the radio telescopes is the resolution that is depending between from the distance between antennas. You see in this slide the radio telescope of Medicina, not far from Bologna in Italy. This is very powerful and interesting radio telescope, but the resolution is very poor, is comparable in the visual light to the resolution of binocular for a family. What does it mean? Okay, if you have a desert, and unfortunately in Italy we don't have deserts, you can have a better resolution. This is the famous VLA in the USA. What does it mean to have better resolution? Look at this image. 85 feet diameter radio telescope will give you this image. 250 diameters will allow you to disentangle some important feature. And finally, 1 mile diameter will give you an appropriate representation of the object in the image. So what about the solution? Solution is very simple to say. Just a little bit more complicated to realize. Is to spread radio telescopes all over the world in order to use the widest possible base. This is called very large base interferometry. Idea is simple, realization is very tricky. Why? Because you have to correlate signal coming from different telescopes with a precision that is comparable to the length, to the wavelength you are observing. What does it mean? This means presently that you pick up the magnetic tapes with your data and send to a central center, that will try to correlate data from different telescopes using a maser source of time. This is very long, tedious, expensive, and put a strong retard time in the results. So the best way is to do it by network. So what about the band required? Very broad band is required. So some experiments have been done, and apparently it seems that could work. This is, well, in effect it is last year's scheme. Anyway, this is the scheme of the network, not of wires, but of radio telescope that will form the European very large base interferometry network. And apparently the existing and forecasted networks is sufficient to do the business. The problem is that the required bandwidth, this is more or less 30 gigabits, is very expensive. And it is difficult to sustain a 24 hours service for all the year. Okay, I am over, and I have tried to see to say some key points of a relationship between astronomy and the grid. The main point is that we no longer works on the networks, but on the application side. And of course, next step is, for example, for radio astronomy is going farther and farther with a grid not only in the world. This is an experiment from NASA, and fortunately we are by default in a pole position in the grid business because of intrinsic nature, grid nature of the universe. Okay. Thank you.
Any questions for Leopoldo? So I'd like to thank you. It's very good to see such a wide-ranging talk about how astronomy needs the grid. Actually, since we're in good time, if you'll permit me, I can't help but add another application-oriented statement. And I'm glad you finish on this slide, so I'll explain to people what this is. I'm a particle physicist. You're an astrophysicist, and these disciplines are very, very close these days, actually. Most of the things they study are completely related. And it's interesting that as time has gone on in the last few years, the more we study, the less we seem to know between us. About 5 years ago, we knew that we didn't know a large amount about what the universe was made of. You know, we thought we knew 10% of it, and maybe 90% of it was dark matter, and we didn't know what it was. And as time has gone on, and this, if I'm not mistaken, is a simulation of dark matter distribution, is that not right? I think so.
Yeah.
I think so. As time has gone on, we now know with great certainty that we know even less about the universe, that only about 60% is matter, you know, and only 5% of that we know what it is. So that means, oh, have the numbers right, but about 50% of it is matter. We know the sort of thing it is, but not what it is. But 40% is something completely different, dark energy, that nobody has a clue what it is. And in particle physics, we've measured things to 1 part in 10 to the 5 in terms of the Z boson, but we still have absolutely no evidence for what gives anything mass anyway, even if we knew what it was. So I can't help but wonder, with all the power that we're going to get from the grid in the next 5 years, just what we won't know 5 years from now. We'll probably be able to really consolidate our lack of knowledge of the universe. But it's a very exciting time for both fields. Anyway, with that rant, I'll finish there, and we'll thank the speakers again, and we get to coffee early.